This new session today, we have Andrea Passerini from University of Trento. He's associate professor there in the Department of Information Engineering and Computer Science. And his main research interests are in the field of machine learning techniques, especially learning in domains with complex structure, relation, and constraints. And he's going to talk about Bayesian networks today and how to use these methods to inference and learning. So, Andrea, the floor is yours.
Okay, thanks a lot for the invitation and for the introduction. So today I would like to give you kind of an overview and some details on how to understand Bayesian networks and how to play with them. Okay. Well, first of all, just quick question: how many already saw Bayesian network in some master course or wherever? One. Okay, good. So the first part is about the representation, okay, and how to basically model interaction between variables with Bayesian networks, and then we will go with the inference and learning, okay? Depending on, let's say that, feel free to raise your hand and say, we know this, so that I can go faster, okay? I have additional material anyhow, in case we decide that some part is kind of easy, or I can go a little bit faster on some parts, okay? Okay, so first of all, just some notation in how to represent stuff. Bayesian networks are about modeling joint probabilities. So I write px, comma y as the probability of x and y. It's raining and it's sunny. Px given y is the probability of x once y is known, probability that it's raining given that it's sunny. And the main rules you use in order to play with probabilities are these three. The sum rule is what's called the marginalization. It allows you to compute the probability of one variable from the joint probability of the variable and others by marginalizing out the others, so summing out over the possible values of the others. And then there is product rule, which relates joint probability with conditional probability, so that probability of x and y is x given y times p of y. And then there is the Bayes rule, which is pretty relevant for Bayesian network, as the name suggests, which allows to invert, okay, conditional probabilities between x and y. So it's easy to derive the Bayesian rule from the product rule. You just put px down, okay? So it's, in a sense, not really an additional rule, but it's so relevant that it has a name itself, and actually it's kind of maybe the most relevant in a sense in terms of what you do with it. So let's say in terms of modeling, the way we understand Bayes' rule and also the reason why it's that relevant is that it allows to invert the statistical connection between cause and effect. Okay? As we will see in Bayesian networks, it's easier to represent the relationship between probabilities as causal relationships. There is a link from A to well, x to y if x is somehow a probabilistic cause for y. And in this case, you can basically represent the relational probability between the variables in this way, meaning that x given y is the likelihood. Okay, if x is the effect that you observe and y is the cause, you can basically represent the likelihood that you see something given a certain cause as the likelihood, okay? Py is the prior probability of the cause without seeing any effect, okay? And px is the evidence, the probability of the effect, being agnostic about the cause, okay? And this operation allows you to derive what we are usually interested in, which is the posterior, the probability of the cause given the effect. If you think of diagnosis, what you're interested is in knowing what is the probability of a certain disease, a certain pathology, given the symptoms. But you usually see the symptoms, not the pathology, right? And now Bayes theorem allows you to do this in inversion, okay? And as we will see, it's also the way you can reason with the probabilistic network made of variables and relationships between them, okay? By the way, the evidence, Px, can always be computed by taking the numerator and marginalizing out the variable which is not in the denominator, okay? So you take Px given y times Py, and you sum over y, okay? And you get Px. Because by the product rule, this is the same as this. And if you sum over y, you get x. Okay? Now, why graphical models? Okay? Meaning that, in principle, you can do probabilistic reasoning, okay, by just applying these previous rules. Okay? You represent everything in terms of these probabilities, and you do some products and so on, and that's it. Okay? So graphical models are in a representational kind of framework and tool, which allows to simplify a lot, quite a number of operations that you can be interested in doing with probabilistic models. Okay? Basically, the first thing is that Bayesian network is a way to visualize the relationship between the variables in terms of connections, okay? And, well, the independencies which are implied by the network are not exactly trivial, but you can read them from the network, assuming you know certain rules, okay? And then it also allows you to decouple the qualitative structure of the relationships, okay, whether two variables are related with each other or not, from the quantitative aspects, which is more like probability distributions, conditional distributions, and so on, okay? And finally, graphical models allow you to devise efficient algorithms for doing inference, so reason about probabilities, exploiting the structure of the graph in order to make this more efficient than if you just did it without exploiting the relationship between the variables, okay? First of all, the semantics, okay? Bayesian network is a directed graphical model, okay? The structure is a directed graphical model. And each node is a random variable in the simplest case, and edges represent direct dependencies between two variables, okay? And the local independencies that are represented in the network, okay, ILG, L stands for local, are these for each node, okay, xi, the node is independent of its non-descendants given the parents, okay? The non-descendants are all the nodes which cannot be reached from the node going down through the arrows, okay? This is what the Bayesian network encodes in terms of local independencies. And this type of encoding allows to as we'll see, to factorize the probability distribution represented by a network in a nice way. So, again, a Bayesian network is about representing the joint probability over a set of variables, okay? Now, if you have a certain probability distribution, okay, this probability distribution implies some independency assumptions, okay? Maybe two variables are independent of each other, or they are independent of each other if something else is given, okay? Now, a certain graphical structure, G, can be used as a way to encode these kind of independencies, okay? And G is called Independency Map, or IMAP, for a probability distribution, okay? If all the independencies encoded in G actually hold in P, okay? Watch out that this is subset X. It's it's not strict, okay? Meaning that it has to be that if you encode an independency in G, this should hold in P, but it's not necessarily the case that all the independencies in P you encode in G, okay? This is, I mean, you would like to do that, to encode everything, and I will be back on that in a bit. But sometimes it's not possible, okay? And still an appropriate, but maybe less, in a sense, efficient representation of the distribution is obtained, provided if there are independencies, they are there, okay? So in a sense, if you think of it, a fully connected graph is an IMAP for any probability distribution over its variables, okay? But not a very interesting one. Okay, now here is where factorization comes into play, okay? And this is what will allow us to do things efficiently. We say that P, the probability distribution, factorizes according to G, okay, if the joint probability over the variables, okay, can be decomposed as the product of the probabilities for each node given the parents of the node, okay? So for instance, here you have that P of x1 to x7 is starting from, let's say, the top part. P of x1 has no parents. P of x2, P of x3, x4 given x1, x2, x3, x5 given x1, x3, x6 given x4, x7 given 4 and 5. Watch out, because sometimes in the slides I leave some errors. Sometimes I do it on purpose because to see if my students are, looking. Sometimes I really forget, okay? So here I remember I had an error, but I think I corrected it at some point because they were always taking it, okay? Now, the nice thing is that if G is an IMAP for P, okay, then it happens that the probability distribution factorizes according to G, okay, as this product. And also, the converse is true, okay? If P factorizes according to the graph, okay, then the graph is an IMAP, is an independency map for P. Okay? So there is this kind of relationship between factorization and being an independency map. Okay? And the first one is pretty easy to show. Okay? So I also have it. I have it the other one, but only in the appendix. If G is an IMAP for a probability distribution, then the distribution factorizes according to the product of node given parents, okay? And this is easy because we know that if G is an IMAP for P, then P satisfies at least these independencies for each node variable. Then variable is independent of the non-descendants given the parents, okay? Now, if I take the joint probability, and I order the variables, okay, in decreasing order, meaning that xi comes before xj if there is a link between I and j. Okay, so I order them as they are here, for instance. Okay. Now I have that the joint probability is decomposed this way. Okay. Consider that, remember that with the product rule, we know that a distribution, joint distribution, can always be decomposed as probability of one variable given the others times probability of the others, okay? And then I can repeat this on the others, okay? So I can produce what's called the chain of the compositions, okay? So this basically is, I take the product over all variables, x1 to xm, of P of xi given what's before, okay? And now, and this is just chain rule, product rule, okay? And now what happens is that if you look at the independencies, okay, xi is independent of its non-descendants given the parents, okay? Everything which is before here, because of the orientation, of the topology, ordering, is non-descendant, okay, is before. So you just need to retain the parents because xi is independent of the non-descendants given the parents, okay? So you can get rid of everything but the parents, and you recover this, okay? So for instance, here you would have, let's say, x6 given 1, 2, 3, 4, 5, okay? These are all non-descendants of x6, okay? But actually x6 only depends on x4, okay? So you can simplify it as x6 given x4, okay? And so on.
Sure that you also have 5.
Yes, because 5 is not, there is a difference between ancestor and non-descendant, okay? x5 is not a non-descendant of x6, meaning that you can't reach x5 from x6 down. It's a little bit tricky, but it has to be. It is true that x6 is independent of x5 given x4. Okay. Actually, in this case, you also have x7 actually, because none of them is reached from x6 down. Okay, and we will see. From the rules of independency, okay, I can come back on this example again because we will see that if you see x4, okay, x6 gets independent of all this part. Okay, I will show you with a very simple rule. Okay, and now with this we have the tools in order to let's say. Introduce Bayesian network, both structure and probabilities. Okay, so a Bayesian network is actually a pair. You have a graph and a probability distribution, P. Okay, and in this pair, P factorizes over G. Okay. And basically, the way you can represent it then is as a set of conditional probability distributions associated to each of the nodes in the network, okay, which represents P of xi given the parents. Okay? And now what happens is that the joint probability distribution, okay, P of xy up to xm is equal to the product of P of xi given the parents. Okay. Now I'm going a little bit fast here because you told me that many already saw these things. Again, it can and it has to be interactive. So if you say, "Didn't understand it," slow down, hurry up, I can do that. Okay. Now, very simple examples just to also show what is a conditional probability distribution. Toy regulatory network, let's say in gene networks, you have A, B, and C, which are genes, okay? And C is a gene which can be enhanced, okay? So its expression level can be enhanced by both A and B, okay? So in terms of causal relationship, you can put links from A to C and from B to C, okay? A Bayesian network doesn't have to be causal. Okay, you could also put links in the other way, but it's usually much more understandable, and we will see also more efficient to try following causality whenever you know that, okay? Or you think you know that. But I mean, it's not illegal or incorrect to put links in a direction which is not that of causality. I will come back on this also later on. Now, this is G, the graphical structure, okay? And now P, as I said, has to be decomposed into the conditional probability distribution for each node given the parents, okay? Suppose that here we represent gene expressions in two levels, active and inactive, okay? In this case, discrete case, conditional probability distribution can be represented as conditional probability tables. Okay, so for instance, A, okay, takes two values, active and inactive, and their respective probabilities are 0.3, 0.7. Clearly, they have to sum to 1. Okay. The other rule of probability that I didn't put there, because I mean this is really a rule for single probabilities, not for combinations, is that when you sum all the values, you have to get 1. For B, it's the same. Okay. For C, this is a really conditional probability table because you have parents, and so you basically take all the possible values of A, active and inactive. For each of them, all the values of B, active and inactive. Okay, so that an entry in the table is basically the probability of C being active given B active, A active. Okay? This one is the probability of C being inactive given that B is active and A is inactive. Okay? So each entry is the probability of a certain value for the variable given a value, a configuration for the parents. Okay? Now, all the columns have to sum to 1. Okay? Because given that A and B are active, okay, C can be either active or inactive. Okay? So the probability of these two things have to sum to 1. Okay? The probability of a variable given whatever sums to 1 if you sum over the variable. Okay? So all of these sum to 1. Now, of course, this is a very simple network, just 3 nodes, but it's also a building block for showing independencies and generalize independencies to larger networks. Now, first of all, what is independence? Two variables are independent if their joint probability is equal to PA times PB. Okay? There is no influence of each other. And two variables are conditionally independent given another one if their joint probability given the other variable is equal to P of A given C times P of B given C. Okay? These two things are different, meaning that it is often the case that two variables are independent but are not conditionally independent given something, or vice versa. Okay? So independency can, let's say, switch on and off depending on what you know in the network. Okay? And we will see how to, let's say, see these in the network. Okay? And independency, of course, it's very interesting in order to understand what's happening, and it's also very useful in order to do efficient inference. Now, the notation is A independent of B given something, so that the non-conditional independence is A independent of B given the empty set. Okay? Now, the way to verify if independency holds is by applying probability rules, okay, in order to see whether a joint probability does decouple in this way. Okay? So you take a Bayesian network, you see how it decomposes in terms of nodes given parents, and you say, okay, let's suppose C is observed. What about A and B? Do they decompose as A given B times A given C times B given C or not? Okay. Now this is true, but it's pretty complex for large networks. Okay, and I will show you a way to avoid doing this and identify independencies just by visual inspection of the graphical model. This is one of the big advantages of the graphical model. Okay, and this will work by building up rules based on simple basic rules and combining them. okay? And this criterion is called D-separation. Now, basically the idea is to start with simple networks, okay? Show rules on simple networks, and then show how to combine these rules, okay? The simplest possible network where you can be interested in discussing independencies is a network with 3 nodes. Because if you have 2 nodes, either there is a link or there is not, okay? So it's trivial. And the other thing is when you have a network with 3 nodes, looking at the fully connected network doesn't make much sense, because if it's fully connected, everything is related with each other, okay? So it has to be a network where one edge is missing, okay? And now let's see what happens depending on how this network looks like, and this depends on the directions of the arrows. Now let's say this first example, okay? I will always represent these examples putting C in the middle so as to have some kind of consistency, okay? So C is the middle node, and then it is connected to A and B by edges, and the type of a structure depends on the direction of the edge with respect to C, okay? So for instance, in this case, C is connected to A by an arrow which has the tail in C and the head in A, okay? And C is connected to B also by an arrow which has the tail in C and the head in B, okay? And so this is called tail-to-tail connection, okay? Because C is connected both with the tail and with the tail. Now, using the factorization property of the graph, we know that the probability of A, B, and C decomposes as PA given C times PB given C times PC, okay? And now, let's say I want to know whether A and B are independent, okay? I can't say, okay, A and B are independent because there is no link between them, because they can be dependent indirectly, okay? And this is often the case. Now, what I can do is to take the joint distribution and compute AB. And by marginalization, AB is obtained from the joint distribution summing over C, okay? ABC, you sum over C, you get AB. Now, if I replace ABC with this, okay, then if the independence hold, I should get this to simplify into PA times PB, okay? And now, at first sight, it doesn't. You could play with Bayes' rule and all kind of operations in order to try simplify things, but you don't get to simplify this into this stuff here, okay? And you don't get to simplify because it doesn't hold. So A and B are not independent, okay? Simple example is in terms of, let's say, diagnostic or reasoning about pathologies. Suppose you have, let's say, cough and fever. Let's say A is cough and B is fever, and C is flu, okay? Which can be cause of both cough and fever, okay? And now if you think of it, if you have cough, then you say, well, I could have fever because maybe I have cough because I got a flu, okay? So the probability of having fever if you have cough increases with respect to if you don't have cough. And this is because indirectly, cough can be a symptom of a cause which is also cause of fever, okay? Right? So you have this dependency. Now, let's say if any other independence holds, and the other type of independence you are looking for is a conditional independence, okay? So what happens if C is observed, okay? And usually when we say something is observed, we put solid color in the node, okay? Now, if C is observed, then you are interested in the probability of A and B given C, okay? And now this is obtained from the joint probability just by dividing by C, okay? Because the product rule says that ABC is AB given C times C. So if I take C down, I get AB given C equal to this. Okay? And now, if you replace ABC by this, you will see immediately that PC and PC cancel out, and you get the result. A given C times B given C, okay? Which is conditional independence, okay? And now this is saying that A and B are independent if C is observed, okay? And again, looking at the example before, if you know that you have a flu, okay, then the flu can cause cough or fever, but I mean, knowing that you have cough doesn't tell you something more about the fever, given that you know that you have the flu, because it's the flu that causes the fever, okay? Then, all depending on the examples, you can also have direct relationships, but in general, I guess you get the example, okay? If you know the cause, it doesn't tell you more about seeing an effect, because the other effect depends on the cause, okay? So in this tail-to-tail case, okay, A and B are not independent, but they become independent if C is observed, okay? Now, there are two other cases, okay, with 3 nodes. I could do the derivation again for the others, but I think, I mean, you got the point. Yes?
Is it true that you can associate the lack of an edge with conditional independence here?
Well, let's say if you have an edge, for sure you have that dependency, okay? Because if 2 variables are connected with an edge, okay, they are dependent, okay? But the lack of an edge tells you only that they could be independent, but if they are or not, and if they are conditional independent or not, depend on the structure. Because I will show you that there are some structures in which there is the contrary with respect to what we see here, okay? So it's not always the case that if you lack an edge, you are independent only if the middle node is observed, okay? This holds here, but there are cases in which this doesn't hold, okay? So actually, here are all the rules, okay? I didn't detail the derivation of the other 2. I can tell you if you want, but it's basically the same reasoning as here. And what happened is this, okay? This is what we already saw, tail to tail, okay? This is without evidence on C, and this is with evidence on C, okay? Now, whoop, bad choice of colors. These are the same color, these are the same color, okay? So in tail to tail, okay, you have that A and B are not independent, but they become independent if C is observed, okay? Now, head to tail is a case in which C is in the middle, and there is an arrow going into C and an arrow leaving from C to B, okay? And I say that by the same reasoning as before, we can prove that A are not independent, okay? And they become independent if C is observed, okay? Same behavior as here, okay? And very simple example is it's cloudy, A. It's raining, C. I get wet, B, okay? If you see that it's cloudy, what do? You take the umbrella. Why? Because you think you could get wet. Not just because it's cloudy, but because it could rain, okay? So knowing that it's cloudy changes your probability about getting wet, because cloudy can imply raining, and raining implies getting wet, okay? So basically, there is a chain of causation which relates the origin, in a sense, to the final effect, okay? And so they are dependent. Now, if you wake up, you look outside, and it's raining, okay? Do you care whether it's cloudy or not? It could be sunny, but if it's raining, I go out, I get wet, okay? If you observe the direct relationship, which is direct cause of the effect, you don't care about the possible cause of that cause because you already saw the direct cause and you know that this will produce the effect, okay? So if the middle node is observed, A and B become independent, okay? Now, there is a if you switch the arrows, okay, B implies C, C implies A, nothing really changes, it's symmetric, okay? So it's not really a different case. I mean, names of A, B, C are conventions. Now, the third case is actually the case in which C is a sink, okay? Arrows goes from A to C and from B to C, okay? It's called a sink. This is, in a sense, the opposite of this. This is tail to tail, this is head to head, okay? Now, in this case, I tell you, these are the same color, these are the same color, okay? If I put the slides online, you will see the colors. I tell you that it's the opposite, okay? That A and B are independent, and they become dependent if C is observed. The opposite with respect to before, okay? And the example here is, let's say you have A is earthquake, okay? B is burglar. C is alarm, okay? You have an alarm in the house which rings if somebody tries to enter the house, okay? But the alarm can ring also if there is an earthquake, okay? Because all alarms ring when there is an earthquake, okay? Now, if you know that there is an earthquake, okay, this doesn't tell you anything about the fact that there is a burglar, okay? Well, if you think of it after the earthquake, maybe there are burglars, but simultaneously, there is no reason, either the burglar is really unlucky or there is no reason why these two events should be related, okay? But suppose that you hear the alarm ringing, okay, in your house. You're sleeping, for instance, you hear the alarm ringing. What do you think? A burglar is trying to break in, okay? Now, suppose you hear an earthquake, okay? Immediately after you hear an earthquake. What do you think? It's not the burglar the cause of the ring, it's the earthquake, okay? Which means that the probability of the burglar goes down because you observe the earthquake, okay? This is called explaining away effect, okay? If you see, there are two causes competing for an effect, okay? Then if one of the causes, if the effect is observed, okay, the two causes become in relation because they are in competition, okay? If one cause is observed, the other cause is less probable, okay? Because you already have an explanation for the effect, okay? So this explanation explains away from the other possible cause, okay? And so, back to the question, in this case, it's the opposite, okay?
So it's like the sum probability is 1. The
Sorry?
conditional sum probability is 1, given the effect. So if you have the conditioning over C, you have the sum of PA given C and B over C. It's 1.
Okay, you have PC given A and B, okay? If you sum over the possible causes, okay, only if you sum over the effect, you get 1, okay? If you sum all the possible causes, okay, C given A and B, okay, you have to, because, I mean, there is also A and B are probabilistics, okay? So in general, the shape of the network, this network goes like this, right? C given AB times PA and PB. If you sum this over A and B, you get PC, okay? Only if you sum also over C, you get 1, okay? If you sum this over C, okay, you get PA and PB, okay? So either they are certain or you don't get 1, okay? Okay, now example of this head-to-head connection, because it's a bit the most, in a sense, maybe unnatural, and it also allows me to show you an example on a full-fledged network. Very similar to the other one. Suppose you have, say, an electric gauge telling you there is fuel, there is no fuel, okay? And the gauge can be up, okay, and down depending of the fuel tank, okay? If there is fuel, it goes up, but also the battery, okay? Because if there is no electricity, the gauge goes down, okay? And now, so the network goes like this. The gauge is in the middle, the sink, and the two causes are battery and fuel tank, okay? And now here you have that, let's say that, so here you have two values, battery flat, battery charged, and say that the battery is charged with 0.9, so flat is 1 minus. The fuel tank is non-empty with probability 0.9 and empty 1 minus, okay? So here I say full meaning non-empty, okay? And then you have the gauge, okay, which is, as before, it should consider all possible cases for the parents, okay? So here you have that, and I only reported here the case in which the gauge is 1. So if with respect to the previous case, I'm showing you this row, because the other one is just 1 minus, okay? And now here you have that if the battery is 1, so charged, and the fuel tank is full, the probability that the gauge is up is 0.8. Say it's not very reliable, or you don't see very well. If battery is 1 and fuel is 0, you get 0.2, much less. If battery is 0, fuel tank is 1, 0.2. If both are 0, you get 0.1, okay? And now, what happens is that if you observe the fuel gauge, let's say if G is 0, okay, so the gauge is down, you are interested in knowing whether the fuel tank is full or not, okay? So you're interested in saying P of F equal to 0 given gauge 0. Should I go and take more oil, or there is something else going on, okay? And now what happens is that here the probability of this fuel tank being empty given the gauge empty, reads empty, goes up, okay? With respect to before. Before was 0.1. Now it goes up to 0.26, okay? Not much, because this is very unreliable, but it goes up because you have evidence telling you that probably there is no fuel, okay? Now, the way you compute this, okay, has to do with inference, okay? Meaning that in the network, you only have this and this. So gauge given the parents, okay? And now if I want to compute this stuff. I can't read it in the tables because it's nowhere in the tables. I have to do some machinery, okay, over the probabilities in order to come out with this probability. Okay? Now, I will not show it on this simple case because we don't have so much time, and I will show you inference on graphical models anyhow. Okay? So by now, trust me that by playing with the rules of probabilities, you can come out with this result. Okay? I'll show you how in a moment. For a let's say, a more general network. Okay? Now, so the probability that the tank is empty increases, okay, if G is observed to be down. And this is reasonable because there is a connection, okay? Now, if you realize that the battery is flat, the battery is down, okay? Now you're interested in knowing what is the probability that the tank is empty given that the gauge rate's empty and the battery is flat. Okay? And at this point, the probability goes down. Okay? It goes down because of the explaining away effect. If the gauge says down, the reason is very likely because it's the battery which is down. Okay? So the gauge has not enough electricity to go up, not because the fuel tank is down. Okay? Now, yes?
In my opinion, it's also interesting to say that this is not going to zero, because it's still probable that both of them would be occurring at the same time.
Yes, it's not...
Although unlikely.
Exactly. It's not going to zero because it's not impossible that both happen together. I mean, you would be very unlucky, but, I mean, if you are... Still possible, and depending on whether you are a person who controls the stuff that you have. Maybe the battery is flat. Maybe you don't control much, so probably also you forgot about, So yes, everything here is probabilistic. Okay, so even the fact that the gauge reads up doesn't mean deterministically that there is fuel. Okay, so the idea here is to have non-deterministic relationships, basically. And this is, in a sense, an important point because, as we will see later, if you say that something is impossible, you should be pretty sure that this is the case, okay? Because otherwise, you break down everything, okay? If you have a large network and there is a very tiny piece of the network in which you say this is impossible, maybe all the rest of the network, the configuration is very likely, but if this is impossible, everything goes to zero, okay? And then maybe you are wrong. It's only very unlikely, okay? Now, there is a bit of an extension here to the head-to-head independency. And it's very simple to show by an example. Remember the example of the earthquake and burglar possible causes for the alarm, okay? Well, suppose you also have, let's say, connection to your cell phone so that you receive a phone call if the alarm rings, okay? And on the cell phone, you see, okay, that the call comes from the system, okay? Now, if you're not at home, and you receive a call from the system, what do you think? A burglar is breaking in my house, okay? Now, if you are in front of television and you see that there is an earthquake taking place in your area, what do you think? You forget about the burglar and you say, wow, there is an earthquake, okay? So, earthquake and burglar become related not only if there is evidence of the alarm, but also if there is evidence of some consequence of the alarm. You didn't hear the alarm, but you received some evidence which is a consequence of the alarm itself, okay? And still, this puts the two causes in competition again, okay? So in this case of the head-to-head, it's a little bit more complex because the two possible causes become related not only if the direct effect is observed, but also if just a consequence of the direct effect is observed. Okay? Maybe they become more loosely connected the farther down you go in the chain, but in terms of there is a dependency or not, okay, observing an effect of the central node will put these two causes in competition, and so they will become dependent. Okay? So the general rule is a head-to-head node C, okay, basically makes the two parents dependent, even if not C itself, by any of its descendants is observed. Okay? So a consequence of C itself. Okay? Now, this is not the whole story because we talked about networks with 3 nodes, and in this last case, how to also read the independency going down in the descendants. But this doesn't tell us what is the independency on a, let's say, entire network of multiple nodes. Okay? And now, there is, at this point, a very simple way to read independencies in the network, which uses these rules that I showed before as building blocks. Okay? And now, if you have any Bayesian network, okay, and let's say A, B, C are arbitrary sets of nodes, okay, non-intersecting. So A, B, and C, okay? Can be 1, 1, 1, it can be sets, okay? And now, it is true that A and B are deseparated by C, okay? If it holds this. Deseparated by C means, in a sense, that C blocks the information flow between the two sets, between A and B. Okay? So it's really a matter of blocking the information flow. Also, visually, you see the network, and you can see information going around the network. Okay? And there are some nodes which block the flow, so that information can't pass if you observe that nodes. Okay? And now here, the idea is you would like to see and to prove that all the paths which connect A to B, meaning any node in A to any node in B, gets blocked by the nodes in C. If this happens, there is no information flow, because somewhere in each path, the information flow is blocked. Okay? So there is no connection of information. Okay? And the two sets become independent. Okay? Now, when is a path blocked? Okay? So first of all, a path is just a sequence of edges and nodes between two nodes, one in A and one in B. Okay? You don't have to follow the arrows. Now, a path is blocked, okay, if it happens at least once over the path that either there is a tail-to-tail or head-to-tail connection going through one node, which is part of the set C, okay? Because in that case, you are here, okay? The path is doing something like this, or something like this. So if the central node is observed, the information is blocked. It's like it's raining. I don't care about cloudy in order to say whether I get wet. So if this is observed, this blocks the information. So along the path, information is blocked. Along the path, information is blocked. Okay? Now, and vice versa, the arrows meet head-to-head, and the middle node is not observed. This case, okay, or this case, okay, there is no alarm, so earthquake and burglar are not dependent, okay, so there is information is blocked here, not because you observe something, but because you don't observe something. Okay? So this node shouldn't be in the set C, and neither should its descendants, because in the head-to-head, as I said, you unblock the path also if some descendant is observed. Okay? So if this doesn't happen, then that path is blocked. Okay? And if all of the paths are blocked, there is no flow, and the two sets are independent given C. Okay? Now, simple example, okay? Let's say the two sets are A and B, two nodes for simplicity, okay? Here there is a path, this is a path, okay? That's a very simple example, I can do others if you want. And here, okay, so what happens is that, let's say that you observe C, okay? Here you go from A to F. This is a head-to-head connection, and C is observed. C is a child of E, so it's a descendant of E. If C is observed, the path is unblocked. It's like I receive a phone call, so earthquake and burglar gets connected as possible causes, okay? And so this unblocks the path, so A and B are not disseparated given C, okay? If C is not observed, if nothing is observed, okay, this path is blocked, and so A and B are independent. Okay? So A and B are independent if you don't see anything. Okay? If you observe C, for instance, this path is unblocked, but if you also observe F, so if you see both C and F, this path becomes blocked. Okay? It's a tail-to-tail, and the middle node is observed. So information goes from A to F, but it doesn't go here up, down to B. And so if C and F are observed, A and B are independent. Okay? And you can do this for more complex networks, okay, and multiple paths with similar reasoning. Okay? This is only reasoning about graphical connections, okay, edges. It's not looking at probability tables, probability distributions, and so on. Okay? This is one advantage of reasoning with Bayesian networks. Now, a little bit of a independency revisited, okay? I said that a Bayesian network structure encodes local independencies, okay? Each node is independent of its non-descendants given the parents, okay? And now, if we go back to the initial question that we had, okay? Here, if X4 is observed, okay, if you see all connection between X6 and the other nodes are either head to tail, like this, or tail to tail. These are both cases in which if you observe the middle node, the nodes become independent, okay? They are these cases. Okay? So this is X6, this is X7, this is X6, and this is, let's say, X3. Actually, this is X6, and this is X3, and so on. If the middle node is observed, the rest becomes independent. Okay? And so if you observe X4, all these are not having any more influence on X6. Okay? Only if you are a descendant of X6, you still have a path. Okay? Open. Okay, now, more general, let's say, notion of independency. A Bayesian network structure encodes a set of global or Markov independence assumptions, okay, which is all the independence that you are in the networks are A is independent of B given C if A and B are disseparated by C. Okay? So, and these you can read by doing this reasoning that I showed before. So all the independents which are in the network are of this type, okay? The local ones, I already said, they are the simplest, okay? Node, non-descendants, parents. Global ones need to do some deseparation reasoning, okay? Note that this kind of independencies will be pretty useful when building inference engines, okay? Because if you need to consider all the networks, all the nodes in the networks when you do reasoning, for large networks, you die, okay? Now, two final things before we close this part about representation. Actually, there is one caveat about these local structures, okay, which is, as I said, the tail-to-tail and the head-to-tail connection both say that if the middle node is not observed, there is a relationship. If the middle node is observed, there is no relationship, okay? If you think of it, this is an identical independence assumption about the variables. All these structures, and here I'm showing the head-to-tail and tail-to-head, both the two symmetric cases, okay? All these are saying that A and B are not independent. They are independent if C is given, okay? Semantically speaking, they are very different because we reason in terms of causality, okay? This is, let's say, cloudy, rain, and getting wet. This is, let's say, flu, cough, and fever, okay? So, in a sense, they encode they tend to encode different phenomena, a common cause, a chain of causation. But in terms of independencies, they're encoding exactly the same thing, okay? This means that an automated system, which has no semantics, okay, cannot distinguish between them, okay? This is actually, these structures are I independence equivalent, okay? They encode exactly the same independencies, meaning that they are the same thing for the system, okay? The only difference is semantic, okay? And as I said, Bayesian networks, they do not reason in terms of causality. You can enforce causality by putting the link in the direction you want, okay? But this is not something the model knows, okay? And indeed, there is no way to infer causality just from data, okay? You can infer independence, okay? And if you have enough data, you can correctly infer independence, but there is no way you can infer causality, the direction, okay? Now, so when you talk about Bayesian networks, you also talk about equivalence classes, okay? Structures which encode exactly the same independencies. So in terms of representational power, they're identical, okay? Two structures are I equivalent if basically they encode the same independencies, okay? For the small structures, there are just two classes, these ones and this one, which is doing something different, okay? Now, if you go for a full graph, okay, also full graphs are, can be broken in independency classes, okay, and equivalence classes, so that instead of having a Bayesian network, you have an equivalence class of Bayesian networks, okay? I will not go into detail. I have the stuff, but I think we can move to something else, okay? But remember that there is this kind of indetermination in Bayesian networks, okay? You can reason and infer independencies. You can't really easily infer directions, okay? You should reason in terms of equivalence classes, okay? Finally, how to come out with the Bayesian network modeling, let's say, your domain of interest, okay? Few tricks and suggestions. Well, first of all, typically you have to get together with a domain expert, because domain expert can tell you what are the relevant variables, what are the possible causal relationships, which are pretty important, and so on. You define variables for the entities of interest, either that can be observed, okay, that you know you can measure, or that you can be interested in predicting, like the diseases, the pathologies, but maybe you can't measure. And also, in some cases, latent variables that you are not that you don't observe, and in principle you're not even interested in predicting, but they can bridge, okay, between these, can be of interest. Okay, so some kind of latent phenomenon, which is in the middle between what you observe and what you'd like to predict. Okay, this is adding expressivity to the model, and in some cases this is beneficial, but it gets a little bit more complicated. Try as much as possible following causality consideration when putting links, both in terms of semantics and interpretation, and also because it tends to produce sparser networks. The less the edges you have in the network, the better, because when you will do inference, you have less channels for passing information, you go faster, okay? And if you have a sparser network, which basically encodes the same information, it's much better, okay? Never, or almost never, assign 0 probabilities to configurations, okay? Because are you really sure that this is impossible, okay? If it's only something that you never observed, okay, I mean, you know by physical reasons that this is really impossible, or if it's only something that you never observed, watch out, because, I mean, you will be using the network in the future, okay? And especially if the network is big, having a single relationship between 3 variables, which is impossible, makes the entire probability go to 0, okay? Maybe all the rest of the configuration is very, very likely, but you are breaking down everything, okay? And then, how do you decide probabilities associated to nodes and to tables? Tricky, okay? You can use experts for this, but typically if you have data, you will do learning to learn the parameters, and I will show you how to do that, okay? And partially, you can also do learning of the structure of the network, meaning the edges, and I will also give you hints on how to do that, okay? Now, I think we can stop now because I'm moving to a different topic. I would suggest to have, if you agree, 2 breaks, one after this, and we go for inference, and one after inference for learning, okay? This is, so maybe the breaks should be like 15 minutes, 10 minutes? 10 minutes? Okay, good.